Thanks everyone for coming to this talk that I've got here. What is Bitcoin? This is a talk geared towards non-technical audiences to help provide an understanding of what makes Bitcoin useful and what the technical foundations are that make that useful. So it needs to be an introduction to some of the core technical concepts, but geared towards an audience who may not be familiar, may not have an engineering background, those sorts of things. So first, who am I? What do I do? What is this talk? My name is Mark Nesbitt. I'm on the blockchain security team. It's a part of the product security team led by Shamik Islam. We focus on what we call protocol to wallet, which casually can be described as secure the crypto, securing the cryptocurrency that Coinbase holds. That means we often work with the crypto engineering team, the crypto engineering org. So if you're familiar with the key management team or the wallets and protocol team or the blockchain team, those are all different teams in the engineering org who work on different systems that support our ability to safely send and receive cryptocurrency and otherwise interact with blockchain networks. As I mentioned before, this is geared towards non-technical audiences, and we'll introduce some fundamental concepts of Bitcoin and by extension other cryptocurrencies. I know most about Bitcoin, although I'm familiar with quite a few. I'm focusing on Bitcoin here. And if anyone has any questions about how other cryptocurrencies may or may not be the same, definitely feel free to ask that at the end, and I can talk about some of the similarities and differences there as well. So, what is Bitcoin? Before I answer, I want to acknowledge that this is a pretty broad, general question. There are many different answers to this question and different takes on it. In fact, Coinbase has an article. If you search what is Bitcoin, and perhaps even just what is Bitcoin in Google, because our SEO is great. But what is Bitcoin? Coinbase will certainly bring it up, where we explain the basics of Bitcoin. And this is a great article. Kudos to anyone who worked on it. My goal isn't to refute those takes or to create an end-all, be-all answer to this question. Bitcoin is a pretty complicated system, and there are lots of components to it. And answering this question, what is Bitcoin, is actually pretty tricky. And I won't have time to cover many important aspects. So my goal here is to provide a lens in which to view Bitcoin, a way of thinking about what it's accomplishing and why this matters and why it has value. And from there, I'll explain a few technical concepts that enable these things. So I just wanted to kind of clear my throat with that and say, like, this is one way of looking at it. It's not meant to be the be-all, end-all. So first, I'm going to provide a definition that answers this question, and then we'll spend the remainder of the time unpacking that definition. Bitcoin is a protocol for producing a unique permissionless transaction history. Let's break that down. Bitcoin is a protocol that produces a transaction history that is unique and permissionless. I've diagrammed the sentence here. They didn't make me do this in school when I was growing up, so this is probably not quite right, but I found this useful when thinking about how to pull apart concepts and understand different ideas. So we're going to use this sentence diagram as kind of our roadmap to answering the question, what is Bitcoin, and understanding this definition. So we're going to start with the Bitcoin is a protocol component. What is a protocol? Well, a protocol is a procedure. Protocols exist everywhere. Anywhere there's been a procedure that you've been a part of, in a lot of senses, you're working within a protocol. So the example I like to give is, driving. I live in California. Driving in the state of California is a protocol defined by the laws of California. There are different aspects to the protocol, right? You can drive through green lights. You have to stop at red lights. If you're turning left into green light, you have to yield to oncoming traffic. There are rules of a protocol that define how an interaction model should take place. In the context of computers, a protocol can kind of be thought of as a language spoken by the computers, in the same way that cars might be speaking a language following the rules of the road, or at least they have this shared understanding and way of communicating with each other. Computer protocols can be thought of similarly as well. Many people may be familiar with HTTP and HTTPS protocols. So if you open up Google Chrome in the browser, it'll often have that prefix, and that you can think of that as a language for accessing a website. And you may be aware that HTTP and HTTPS are very similar, but HTTPS is secure. So it's a slightly different protocol. There are two different protocols. You can think of it that way, as they have two different languages and two different ways of, two different rule sets. In the case of Bitcoin, it's an open protocol. So the code is open source. So in the same way that the laws of California are accessible and readable by anyone who wants to read them, the code for Bitcoin is open source, and you can go read that code. There are also multiple implementations. There is one main implementation, but there are multiple ones, and anyone could write their own because the rules are laid out and clear, and it explains how to interact. So Bitcoin is a protocol. It is a protocol for producing a transaction history. So let's talk about that part. Transaction histories exist everywhere. You're probably very familiar with them. Your own bank account has an individual transaction history that is specific to you. Your bank or PayPal maintains a transaction history for all of its customers. So you can think of your personal transaction history as a filtered view of that global transaction history. A payment system's transaction history will define all of its account balances. So if we know some initial state, like maybe nobody has any funds, and then transactions occur that introduce funds into the system, or if we have an initial state where some people have funds, if we know the entire transaction history, we can determine everyone's balance. Here's an interesting point that I'm going to come back to later, but it's worth realizing now. There is an infinite number of possible transaction histories within any sort of system that's tracking transactions. And there are different scopes to this. There's the validity of a transaction history. So you have to have enforce certain validity rules. So if you imagine like invalid transaction histories where the same $50 was spent in two places, we could consider that a transaction history that's invalid. And so a subset of those would be the ones that are valid. But within that set of valid transaction histories, there are also an infinite number of those where any type of transactions could have happened. So two different transaction histories. One might have Alice paying this $50 to Bob. Another might have it paying to Charlie. And which transaction history we're going to consider as true is obviously very important to both Bob and Charlie. So we'll return to that. But keep that in mind, that we need to realize that there are a lot of possibilities, an infinite number of possibilities of transaction histories. Okay, so we talked about Bitcoin being a protocol. We talked about Bitcoin producing a protocol that produces a transaction history. This transaction history is unique and permissionless. This is where things get interesting. I mentioned protocols. Hopefully we understand that, what a transaction history is. Hopefully we kind of understand that. But this is the juicy part. But what's interesting here is either of these things on its own isn't particularly special either. Uniqueness is a requirement for any functional transaction history. You can double spend money otherwise. The same way I said, we have two possible transaction histories where Alice may send $50 to Bob in one and $50 to Charlie in another. Depending on who's viewing these histories, you may be able to spend that $50 in two places. If you could get Bob to look at the one where Bob receives it and Charlie to look at the one where Charlie receives it, maybe Alice could get away with spending the same $50 twice. So if it's going to be functional, it needs to be unique. We have to be able to agree on one. It can only be a single transaction history. And permissionless transaction histories exist anytime a transaction system doesn't have a controlling authority. So for instance, cash is one way to think about this, where we don't know the transaction history of the bill, but we know that there is one because it physically exists and it moved around and it changed hands. And it's a little hard to stop cash from changing hands. So we can think about that as somewhat having a permissionless nature. Certain physical transaction systems, such as gold, I mentioned cash, or other precious items, can be considered to fit this description as well of being both unique and permissionless. So in the case of gold, let's imagine that. A chunk of gold only exists in one place at any given time. So sort of the nature of reality, I guess you could say, enforces the uniqueness of the transaction history that is the ownership of gold. And then the permissionless nature I alluded to a little earlier with cash. Like if you physically possess an item, it's difficult to prevent you from transferring it. There can be laws against these things, but they're a little trickier to enforce when when there's this physical nature of possession, right? Like if PayPal wanted to stop transactions from happening on PayPal, that's pretty easy for PayPal to do. To stop gold transactions from happening, it's much more difficult, and it requires laws. Bitcoin accomplishes this combination digitally, and that's part of what makes it so special and impactful. We're going to talk about how it does that. So I mentioned that this talk is meant to provide some of the technical foundations. This is where we get into some of the technical foundations. Hopefully now motivated to understand why this matters. So they're done. Here's how this is done. Unique is done with proof of work or mining, and we'll talk about that. And the permissionless aspect is done through public key cryptography. We're going to talk about the permissionless nature and public key cryptography first. So public key cryptography is a type of cryptography, and cryptography is a way to use math to encode different values in ways that provides properties of those values. So typically, that secrecy is the property that most people care about. You can encrypt a message and it be secret, and you can share the message with anybody you want to, and as long as they don't have a particular secret key, they won't know what the message is. So it's important to realize that cryptography at its base is math and numbers. In the case of public key cryptography, you create a number, or you pick a number, a very, very large number, and that's a private key. And from that, you can derive a public key. And if you follow this system, you can get some very good properties. So for instance, public key cryptography is typically used for encryption. You can share the public key, and it's impossible to derive the private key. So you can keep one of these numbers secret, one is public. With the public key, anyone can encrypt data to you. That is, make it secret, and then share that encrypted data with the world, and nobody but you can know what the actual value of the data is. It requires the private key to decrypt. Similarly, you can, or actually an analogy for that, I think I found to be very helpful, is public key cryptography is a lot like having a large number of combination locks that are unlocked. So imagine one where the handle is like loose and sliding, and you could lock it around something. You could distribute a bunch of these to your friends and family, and only you know the combination. But because it's unlocked, they can still lock something with it. So they can put a secret message in a box, lock it with the combination lock, and know that only you can unlock it because you're the only one who knows the combination. There's another, besides encryption and decryption with public key cryptography, you can also do something called signing and verifying. And that's similar in the sense that you're still distributing the public key to everybody, and only you have the private key. But with the private key, what you do is essentially you do a mathematical operation called producing a signature, where you have a piece of data and then a signature. And with the public key, you can prove that the signature could only have been created by the person who holds the corresponding private key. So it's a way of validating that a message originated from somewhere. And so the analogy there is in the name. It's a signature. If you think about someone's signature, the theory, I know that signatures can be forged, but the theory of a signature is that only I signed it with my name. It's my John Hancock. Everyone else can recognize it. Everyone can validate that it's mine, but no one else theoretically could create it. We do this mathematically, and it's much better than actually signing paper because there is no ability to forge. So that's a fundamental concept that we use here. Let me explain how it gets used in Bitcoin to create the permissionless nature. The account number, if you imagine your bank account, a transaction history has to have some sort of identifier. Who owns this, right? Who's this transaction to? The account number in Bitcoin's transaction history is essentially assigning Bitcoins to a public key. And then the corresponding private key allows sending from the account with a digital signature. So a transaction in Bitcoin is assigning the Bitcoins to a public key, and you do that with the private key used from where the Bitcoins currently are assigned. So it's a reassignment. And this authorization is the digital signature, and it doesn't reveal the value of the private key. So let's visualize this. We have Bitcoins in the box on the left. Bitcoin that's assigned to a public key that's owned by Alice. Every public key is derived from a private key. So Alice has a private key. She can create a transaction where she reassigns these to Bob's public key. So she goes out and gets Bob's public key and say, Bob, where do you want these Bitcoins to go? And so in this data bundle that is the transaction, she puts Bob's public key in there, and then she signs it with the private key. Notice that this doesn't reveal the value of the private key. So she can do this many times, and no one else can do it. Only she can. And that is a transaction to Bob. And Bob likewise can do the same thing. Now that he's got these Bitcoins, they're assigned to his public key, he can get a public key from Carol, create this data blob where he's assigning it to Carol, and he can sign it with the private key associated with the public key in the orange box. To break this down a little bit more, we can talk about how this works with Bitcoin specifically, and how you spend Bitcoins. You may have heard about inputs and outputs to Bitcoins, or unspent transaction outputs, UTXOs. And so that's what this concept is here. So Alice may have gotten 50 Bitcoins at one point. Maybe she was an early miner, and that was the mining reward in the beginning. So she says, I'm going to make a transaction. I'm going to take this input, which identifies the 50 Bitcoins that I had, and I'm going to create the following outputs. 1 to Bob, rather to Bob's public key, and 49 change to myself, to my own public key or a different public key that I have. And I'll sign it with the private key associated with the orange box. And then notice at signing, the balance, we can consider for now the balance to change. We'll get more into that, but that is the authorization for the transaction. And these chain together. You can see how this transaction history can evolve, because now there's this 49 BTC change output. It's the change output that's here in green, but now it becomes an input to a new transaction. And she can say, all right, I'm going to send 1 Bitcoin to Carol's public key, and then I'll take 48 back for myself. And Bob could do the same thing with his output. With this 1 BTC, he could chop it in half and send half back to himself, half to Carol. And then once they both sign it, we'll see that we can consider Carol to have 1.5 Bitcoins, 1 from Alice and 1 from Bob. And notice that this authorization comes with the private keys associated with where the Bitcoins were assigned prior to these transactions being created. So the Bitcoin ledger is the result of all these transactions and who owns what. So this comes back to this permissionless nature. No one can stop you from creating and using your keys. I mentioned it's just math. You just generate large numbers. From these large numbers, you do mathematical processes and you create a public-private key pair, and you can sign and you can receive, you can share your public keys. And all of this is done by you with software that implements mathematical principles. You don't have to go to any central location or ask anyone for permission to be able to do this. You just have to make an agreement with someone who wants to send them to you. It's peer-to-peer. Okay, so that's the permissionless nature, founded on public key cryptography. Now, the unique nature. Public key cryptography existed before Bitcoin, but a lot of the innovation with Bitcoin is what provides this uniqueness, the proof of work, mining. Okay, so for a transaction history to be useful, you have to agree on one amongst all the participants that want to transact. So the validity rules that I mentioned can be encoded in the protocol in the same way that we've encoded don't turn left in front of traffic into the protocol that is the driving rules in California. We can have a validity rule that says, you must have the same number of coins in your balance that you want to spend. You can't spend more than you have. So we can have this capability of all the participants in the system to consider all the same transactions valid or invalid. However, I mentioned before, there are an infinite number of valid histories. So I could right now send money to anybody on this call, but if I only have $10, I can only send $10 to one person. And I could create different transaction histories where it goes to each one, and any of those on their own could be valid. So there's an infinite number of valid ones to the exclusion of the others, but we need to achieve a unique one. So everyone has to agree on the history of transactions, but we can't have this come from a central authority without loss of the permissionless component that I talked about, that we've gone to all this trouble with public keys to create. In the case of your bank or PayPal, this is how we have a unique history. PayPal says it's the history. They keep track of one, they update it, they're the stewards of it, and we trust them. But the permissionless nature would be lost in that case because PayPal is the arbiter of this system. So Bitcoin's innovation is sometimes described as a decentralized way of ordering transactions, simply placing them in order. And if you can place them in order, then it's easy to apply this first bullet about what's valid and invalid. But the difficulty is, did I pay you first or did I pay somebody else first? So how is this done? The way it works in Bitcoin is transactions are bundled into batches. The batches are called blocks. The transactions contained in a series of blocks, which are called the blockchain, defines this canonical history of transactions. So here we have this transaction we looked at before. Alice spending 50 BTC, 49 back to herself, 1 to Bob, and she signed it with her private key, so it's valid and authorized. And so that'll be bundled into a batch, which is represented by the green box, and then these batches can be chained together. But many different blocks are possible, right? An infinite number of valid transaction histories. How do we agree on the unique one? For instance, Alice could easily sign 2 transactions that spend the same 50 BTC. 1 to Bob, 1 to Dan. We need the uniqueness to prevent this sort of behavior. How do we do this? The answer may not be intuitive, but we do this by making valid blocks difficult to produce. Why does that matter? Why does this solve our problem? Valid blocks are difficult to produce. Then we can add a new rule to the protocol. And the rule is that the longest series of blocks defines our unique transaction history. Length is a number. It can be sorted, and there can be a longest one, which is unique. The max of a set is unique. So when we're looking at all this infinite number of possible transaction histories, we're going to take the one that has the max amount of blocks. And that is very difficult to change, because then you have to do even more work in order to change it. So this simple rule, by making blocks difficult to produce, I think somewhat counterintuitively, at least to me, allows us to have a unique transaction history. Let's talk about what makes blocks difficult to produce. And introduce a concept called a hash function. A hash function has a lot of different properties, but it has an input and an output, like any function. The output does not resemble the input. It's it's pseudo-random. But the output is deterministic. It's not random, because random means you might get different things every time. You always get the same output for any particular input, but the output doesn't resemble the input. The smallest change to the input completely changes the nature of the output. So that's what these first 2 lines here of hash of long number of zeros and a long number of zeros with the last one being a 1 is meant to illustrate. The 2 outputs have nothing to do with each other. It can ingest any amount of data or any kind of data. So a ton of data, like gigabytes, doesn't matter. A single byte. And it cannot be reversed. Because the output is this pseudo-random noise, essentially, you don't know what was hashed when you look at the output. So this is a hash function, and they're key to being able to make blocks difficult to produce, which allows the unique transaction history. Let's imagine we have some data, and then we're going to concatenate a wildcard, so like some extra data, but it's not data that we particularly care about. We have the data that matters to us, and then we have like space for a little bit of extra stuff. That's the wildcard. And we're going to hash the 2 of these together. You can cycle through the wildcard. You could just count up. Maybe the wildcard is just a number that you're counting up. And if you ever get an output, like the 4th one on this row, that has a bunch of leading zeros, for instance, but it could be any number of, it could be a leading pattern, something unique. You know that you had to try a large number of wildcards, far more than 5, actually. This may be a little misleading to think that you can get it so easily with 5. You're going to have to try a large number of attempts, since you can't predict what this output's going to look like before you actually perform the hash function. So you know that someone iterated through a lot of wildcards if you see all of these zeros. And if somebody wants to prove that they iterated through a lot of wildcards, all they have to do is just show you the one wildcard that has all of the zeros once you hash it with the data. So hash functions are quick to perform. So I'll just give you my data and wildcard. You can hash it. The hash function is open source and available for anybody to run. And you will see, wow, there are a large number of leading zeros. The conclusion there is that you tried a large number of wildcards. So you can prove the difficulty. Another concept here that we're going to combine with this is the idea of linking hashes together. You can have a hash of certain data and you get some kind of result. And if you use that result as your next wildcard, you concatenate it with some more data. You can hash it and get another result, and you can create kind of a chain of hashes here with the property that they rely on each other. If the first data gets changed, that first result will change, which means the input to the second one will change, which means the second result will change. And you can chain these together. So if we combine these two concepts into proof of work, and proof of work here, POW, is our hash function, but you have to do it many times. And so if you do data 1 with some wildcard and you get these 4 leading zeros, then you clearly tried a large number of wildcards. And you can put this output that proves that you worked hard on the first iteration as the wildcard on the second one. And you have to iterate again with a different wildcard. Sorry, you don't have it as the wildcard on the second one. I misspoke there. You have it in with the data payload on the second one, and you have a wildcard elsewhere that you're iterating on the second time. And then so you iterate many times. That's what the proof of work function, the POW function, means. And you have an output, again, with a large number of zeros. So each step, it's provable that you worked very hard to get to get that output of that step. But you also have the property that they're chained together. So if the data in data 1 were to change, it would break the chain. So what this means is that if you do this with blocks, and each block has to have a wildcard where you've iterated over the wildcard in order for the block to be considered valid, it becomes difficult to change these blocks. The block that's second to the top might be hard to change, but the block that's buried even further is essentially impossible to change because it's buried under so many iterations of this process. And changing the one on the left means you have to rewrite all of them and find the wildcards to all of them. So this is how it could look in a Bitcoin block. You have the block information, that includes the transactions, and you have your wildcard. And you iterate through it, and eventually you're lucky enough, you find a wildcard, and the block will only be considered valid if it has these leading zeros that are sufficiently long based on the protocol's parameter for the difficulty. Once you meet that requirement, meet that bar, you can share that block with the network at large, and the network can perform a single hash function, validate that you did this work, and then can add this block to the blockchain and extend the blockchain and add the transactions in this block to the canonical unique transaction history. So let me recap that component. How do we get a unique transaction history among all the possible infinite number of valid transaction histories? We do this by introducing this counterintuitive rule. Blocks are hard to produce. When you do that, then you can create this property of chaining blocks together and defining the longest chain as the valid transaction history. And that sorts beautifully into an order where you can define the highest one, the longest one as the canonical one, and we have a single unique one. And now this single unique history is very difficult to change because you have to compete with all the work that went into making it. So these are the two characteristics that I think make Bitcoin transformative. It's unique and permissionless. So to recap, Bitcoin is a protocol for producing a unique and permissionless transaction history. There are many other aspects to Bitcoin. Like I mentioned before, this isn't meant to be the end-all be-all definition of Bitcoin or the only way to look at it, but merely a lens through which you can view it. I think it's worth concluding on a bit of a so what, who cares question. Why does this matter? Why isn't this just some academic definition? I wrote this presentation before the coronavirus came around, so I don't mean this to be an insensitive comparison or a difficult topic, but I've always thought of Bitcoin somewhat similar to a virus. And the reason I think of it that way is that it moves under its own power, right? If we think about our situation today, if we leave our society to just operate the way it is, the virus will continue to spread and move. Essentially, in some ways, you can imagine of its own volition, if you want to frame it that way. And I think of Bitcoin similarly as sort of moving under its own weight. It's like a boulder rolling down a hill. It's created a system where it provides a service. It provides a unique permissionless transaction history. This is a service that a certain number of human beings want to participate in. They want to make transactions with these properties, unique and permissionless. And Bitcoin provides that service, and it incentivizes people to provide that service, to mine and be miners and host this. And as more people want that, the network effect grows, and it grows under its own volition, and it, again, like a boulder rolling downhill. I think it's also worth thinking about the consequences of this idea that it's moving under its own gravity and its own weight, and somewhat sort of unstoppable in a certain way. In the same way that the printing press freed ideas and allowed them to no longer require the permission of the halls of learning and power, I think of money and Bitcoin having a similar relationship. Right now, money flows through the halls of power. That's the way our society is structured. And Bitcoin is a way to break that model. And because our current system is not unique and permissionless, but Bitcoin is, and Bitcoin is spreading, similar to a virus, under its own momentum. So that concludes my talk. I hope everybody enjoyed it. Thank you, everyone, for your attention.